Welcome back, Night Owls. This is Dr. Nighttime, and tonight, we're going overboard a little bit. What do I mean by that? Well, this problem was inspired by a problem that came up on the homework assignment of one of my students. The student was in regular old high school statistics, just below the AP level, actually. And occasionally, when you're in the line of work of private tutoring, you'll get this one question where the instructor hadn't thought through all the details and accidentally asked something that was not solvable at the level of the class. So tonight, going through it and solving it to the best of my ability. This question gets so weird, it actually can't be solved exactly with the numbers given, and it's a matter of finding a good enough model or approximation to just come up with something. In this particular case, this student was learning about central limit theorem and application of the normal distribution, but as it turned out, the problem that she was given involved data that were too skewed to use the normal approximation. So let's get into it. The original problem statement: a fire insurance company insures 1,000 households from a population where most households do not incur fire damage. Imagine that. Imagine living in a place where most houses don't burn down in any given year. The average amount of fire damage is $250 in a given year, and says the standard deviation is $5,000 per year. And this question had two parts. Part A, what's the probability that these 1,000 households that are insured will average more than $300 between them in fire damages? And part B, what net premium should be charged to have a 90% chance of covering the risk, or what insurers would call what is the 10% value at risk. Now, some basic assumptions to make. Assume that the 1,000 households insured, that their losses are independent and identically distributed. I know often, specifically with fire insurance, if you're insuring in a given region, if there's one major fire that burns down a bunch of your houses, it'll burn down the other bunch too. But we're assuming independence of houses and that they're identically distributed. So what was this student supposed to do? This student was supposed to say, all right, we're averaging together 1,000 random variables. The mean is the same as the underlying mean. The standard deviation gets divided by the square root of your sample size. You're supposed to say normal distribution with a mean of $250 and standard deviation of $158 and like 10 or 11 cents. And if you crunch the numbers on this, you actually get either a 57 or 62% chance of the underlying mean being more than 300. And I'll talk about why you get two different possibilities. You shouldn't. In a moment, I'll talk about why there are those two different answers. And for the 10% value at risk, you get about 450. But something goes wrong. When you look at the normal distribution with these parameters, right, this mean, this standard deviation, you get a graph like this. And in particular, you get a sizable probability, not like 80% or anything, but a noticeable probability of these 1,000 households combining for negative damages. Clearly that can't happen. And so it's also entirely possible that what this student was intended to do was graph this normal distribution, look at it, realize what was going wrong, say that the standard deviation is more than 1/3 of the mean, and we have that property with a random variable that must be positive, then there's no hope of the normal distribution actually approximating it well. This little tail area here adds up to about 5%, and that's why you had those two different answers of 57% or 62% getting an average loss above 300. Because when you're setting up what your lower bound is, often you'll say, well, I could go all the way down to negative infinity, in which case you'd be including this 5%, and you'd get 62%, or you could say, well, I know realistically and physically that the losses can't be below 0, so I can just look between 0 and 300. And you'll get like 57%. And if you get something where those differ by more than like 0.00001 anyway, then you can't be using the normal distribution anyway. And so it's entirely possible that my student was just supposed to look at that and say that is the answer. And I did tell her, it's possible that that's what your answer was supposed to be. Go ask your instructor about it. But then in the original problem, right, the exact statement did talk about how the underlying distribution was heavily skewed. Now, often what they teach you is that when your sample size is above like 30 to 50-ish, then it doesn't matter how skewed your underlying distribution is, and then you have a large enough sample to just do a normal approximation anyway. And my sense is that's the direction the instructor was going, especially for asking two different questions, right? One about tail value at risk, and one about probability of an average loss exceeding 300. Now, suppose there weren't that built-in rule that these numbers had to be positive anyway. Now, suppose these numbers were measuring some quantity that didn't have to be positive, or at least non-negative. Suppose negatives were allowed. That wouldn't suddenly make the normal distribution be a better fit. So there's something else going on that would get in the way here, and it deals with the skew of the underlying data. Now, typically at the high school level, they don't teach you how to calculate the skew. And so I made sure to ask my student, by the way, have you learned how to numerically calculate a skew? She said no. And I believe my next words were, excuse me a moment. And then made it clear that my frustration was not with the student, but with the instructor, who did not explain how to go through what I'm about to, and gave her this problem anyway. So generally what they will teach about skew is that if you have curves that look something like this here, you'll have positive or right skew, and if you've got a bunch of higher numbers with some really, really low number tails, right, that'll be a negative skew or a left skew. Okay, in this case, we've got a right skew, so our skew will be a positive number. And so let's talk about how to calculate it. Yeah, so the skew is calculated by taking the probabilistic average of your number minus the average cubed, all divided by the cube of your standard deviation. And the other property about skew that you should know about is that when you're averaging together some number of independent, identically distributed random variables, the skew of the aggregate average will equal the skew of the underlying distribution divided by the square root of your sample size. And so obviously this underlying distribution would need a massive skew so that even when you divide by the square root of 1,000, you're left with something too big. Generally, if your end result skew is between like negative a third and a third-ish, or some would say negative square root of a tenth to square root of a tenth-ish, that would be good enough to use normal approximation. And so, since they didn't give us the skew, let's come up with some sense of what the skew could be, right? Suppose that the reason why you've got this mean, this standard deviation, is that almost all of your houses don't catch fire in a given year, and when they do, they incur absolutely massive damages, and that when you take the average, you multiply that low probability times the massive damages, and that will happen to get you 250. Okay. Based on that, if we let P be the probability of a house catching fire and having major losses, and X be the major loss, P times X is going to be 250, fine. Under that model, where you have a whole lot of zero losses and a whole lot of identical losses of value X, so we've essentially got a scaled version of the Bernoulli random variable. We'll just manually take the expectation of loss minus average loss of 250 quantity squared, and set that equal to the square of our standard deviation, or 5,000 squared. Alright, we crunch that out, FOIL everything out. Notice that we've got a minus p times 250 squared and a plus p times 250 squared, so those can just cancel. And when we have this line here, once we remember that p times x is 250, so this px squared just becomes 250 times x. This 500 times p times x becomes 500 times 250. We've got this equation where x only shows up once, and we get that x is 100,250, and that p is 1 over 401. So, to recap, all we've done here, we haven't actually calculated the skew. We don't even know for sure that this is what's going on. We're coming up with a model where we'll say one of the ways of getting average of 250 and standard deviation of 5,000 will be if out of every 401 houses, 400 of them don't burn down, or don't have any losses, and one of them has a major loss that costs $100,250. Notice that we're pretty much approximating this situation with a binomial. Right now we are saying we've got 1,000 trials, each with a 1 in 401 chance of a success of burning down. Now the other rule that they'll teach you is that the number of successes and number of failures would each have to be at least 10. And so according to this rule, you would need n to be at least 4,010, or you need a sample size of 4,010. Since you don't have that, you can't actually use the normal distribution. And that comes from making sure that your skew is sufficiently small. And sure enough, when we calculate out this skew for a single variable, we get a skew of approximately 20. It's like 19.95. And when we divide that by square root of 1,000, we get a skew of like 0.631. Remember, we want it to be like 0.3-ish. And notice, if we quadrupled our sample size from 1,000 to about 4,000, that would cut the skew in half. That would get it around that range, and then that would be around the cutoff. So we kind of see how this all works. So we kind of see how these different approaches work together. And so now, if we go further with this model of assuming that there's this small probability, about 1 in 400, of a house burning down, and if it does burn down, it'll cost about $100,000. So now we're essentially turning the problem into asking how many of these 1,000 houses might burn down. And so now we're looking at something closer to what's called the Poisson distribution. Again, they can't teach the Poisson distribution at this level, because the probability mass function for the Poisson distribution involves this number E, and they don't teach you what E means or how to calculate E in this class. That's a limits thing, that's a pre-calc thing, and that's considered too difficult for this class. But we're going overboard here, so let's go overboard. Note that of the two questions that were asked, first, the probability of incurring at least $300 as an average loss, well, that's the same as asking, what's the probability of incurring at least $300,000 of total losses? Which is kind of similar to asking what's the probability of getting at least 3 houses to burn down. Slight modification off of that. Remember that this is just an approximation. If we're asking what's the probability of getting at least $300,000 in losses, and you say there's this probability of like 21.4% of getting exactly 300,000, that doesn't mean you include all of it because you said at least. No, it means 21.4% chance that according to our model, our losses will be pretty much 300,000. Assume some randomness in there and that half of them will be above 300,000 and half of them will be below 300,000. Yes, that really is an approximation technique that you can use, and there's a variant of that you could introduce at this level of class. But under that model, you actually get like a 65% chance of incurring less than $300,000 losses total amongst the 1,000 households. The other question, remember, it asks for that 10% value at risk. What's the 90th percentile of the total losses? Well, if you ask, well, what's the 90th percentile of the houses that were burned down? When you start adding these up, you get that you reach that when x equals 5. That would mean 5 burned down houses that would each cost about $100,000 in damages. So those $500,000 across these 1,000 households, yeah, you get that you should be charging at around $500 per household to cover your 10% value at risk. Now, I will say, I probably haven't gone overboard enough, believe it or not. More realistically, rather than saying, if a house has damages, we know exactly how much the damages are going to be, it's actually more common practice to say, if the house has damages, assume that the damages will be exponentially distributed with some mean. And to be brutally honest, the only reason I haven't gotten into that is because I don't remember the exact details of how to go through that sort of Poisson exponential aggregate loss model. And I wanted this video out sooner rather than later. But there's definitely further down that rabbit hole you could go. Until next time, this is Dr. Nighttime wishing you a good night.